Okay, so we've all seen those crime shows, right? The CSI team swoops in, finds like one perfect fingerprint, swabs something mysterious,
Uh-huh.
and bam, before the next commercial, they've got the DNA results, the suspect, probably even a confession. It's all wrapped up neat and tidy.
Yeah, it makes for great TV, definitely. But the reality of forensic investigation, it's it's this constant balancing act between needing answers fast and needing them to be absolutely certain.
Right.
Every single step, from the second an officer puts up tape to the moment that piece of evidence gets shown to a jury, it's incredibly fragile
Hmm.
and incredibly meticulous.
Right.
So today we're really diving into those essential procedures, the science that makes sure evidence holds up, and maybe how new tech is trying to close that gap between TV speed and real world court certainty.
That tension speed versus certainty, that seems key. We're going to unpack things like the chain of custody, why that's so non-negotiable.
Absolutely critical.
And the amazing stories you can get from tiny bits of trace evidence and these newer ideas about getting forensic intelligence faster.
Yeah, our goal here is really to give you the why behind it all. Why following procedure is everything, how they collect and check scientific evidence, and honestly, how just one tiny mistake, one slip up in that chain can basically make an entire case fall apart.
Doesn't matter how good the evidence looks, right?
Doesn't matter at all if you can't prove its integrity.
Okay, let's start right at the beginning then. The crime scene itself, investigators show up, obviously first aid, making sure everyone's safe. What's the next absolute priority?
Setting the boundaries, that's huge.
Yeah.
They find the main area, the what we call the focal point, where most of the activity seems to have happened.
Okay.
And then they move outwards from there. They have to rope off an area big enough, maybe even bigger than they think they need, to make sure all the potential evidence is inside that initial perimeter.
Why go so big initially? Why not just focus on the obvious spot?
Because it's a one-way street, really. You can always make the scene smaller later if you realize, okay, this area isn't relevant.
Uh-huh.
But if you draw that line too tight at the start and then realize, oh, wait, there might be something out there.
Too late.
Exactly. It could be trampled by first responders, washed away by rain, just lost. You get one chance to preserve it properly, and you can't risk losing something vital because the tape wasn't wide enough.
And you mentioned safety first. It's not just about maybe the perpetrator still being around, is it? There are other dangers.
Oh, absolutely. Before they even really start processing, they're looking for immediate hazards.
Hmm.
Things like weapons left behind, of course, but also biohazards, chemical spills, maybe even deliberate traps.
Wow, okay.
Once all that's clear and the scene is secure, then the documentation starts. And it's exhaustive. High-res photos, video, sometimes those cool 3D laser scanners to map everything spatially, plus detailed sketches, diagrams, really capturing the context of everything.
So that preserves the where. But what about the what? The evidence itself, especially biological stuff like DNA. How do they make sure that doesn't get ruined?
Yeah, biologicals are tricky. The main enemies are moisture and contamination. If something wet is collected, say a bloody piece of clothing, it absolutely must be air dried first.
Air dried, okay. Not put straight into a bag.
Definitely not a plastic bag, no. Once it's dry, it has to go into something breathable. Think paper bags, cardboard boxes, plastic traps moisture, and that leads to mold, bacteria. Basically, it destroys the DNA fast.
Right, makes sense. Okay, so that careful handling leads us to maybe the most critical piece of paperwork in this whole process. The chain of custody, the CC. What's the core idea there?
The chain of custody is, simply put, the life history of that piece of evidence. It's the documented, unbroken record of who had it, when, and what they did with it.
Okay.
It has to prove three things to the court, basically. One, that the evidence is real and connected to the crime. Two, that the item presented in court is the exact same item they collected at the scene. And three, crucially, that it hasn't been tampered with or altered in any way while it was out of sight of the court. It has to be in its original state, essentially.
It sounds incredibly strict. Our sources have this example, like a simple drug sample. It goes from Officer Ramsey, who finds it, to Fred, who transports it. Paul receives it at the lab. Derek analyzes it. Evan reviews it. 5 people.
Yep, and that's a perfect, simple illustration. Every single one of those 5 people has to sign that custody form in order, documenting exactly when they got it, what condition it was in, what they did, and who they gave it to next.
And just signing isn't enough.
No way. Every single person in that chain has to be ready to go to court and testify under oath about what happened to that evidence while it was in their specific possession. If just one signature is missing or someone can't account for it,
The chain's broken.
the chain is broken. And that evidence, no matter how incriminating it seems, could be ruled inadmissible, thrown out.
Okay, now here's where it gets really interesting with modern tech, right? We're moving from physical evidence with paper trails to, well, phones, computers, servers, gigabytes, terabytes of digital data. How does chain of custody work for that? Data can be copied, changed.
That is a huge, huge challenge right now. The standard digital forensics practice involves making an exact copy, an image, of the device's storage, and then calculating what's called a hash value.
Like a digital fingerprint.
Exactly. It's a unique code based on the data. If the data changes even by 1 bit, the hash value changes. So that proves the copy hasn't been altered since it was made,
Right.
but it doesn't perfectly replicate the physical chain, proving the original data on the original device wasn't tampered with before imaging or tracking subtle metadata changes.
Yeah.
It's not as robust, especially for international legal standards. It lacks that sort of universally accepted sequential integrity of the signed paper form.
So digital forensics is kind of chasing that same level of tamper-proof, universally accepted proof that the physical CC has.
Precisely. That's why you hear about research into things like blockchain or NFTs, not for money, but using that underlying technology, the immutable distributed ledger idea.
Ah, okay.
The hope is to create a kind of digital certificate of authenticity that's mathematically impossible to tamper with, globally verifiable, time-stamped, something that proves beyond doubt that the data seized is the exact data analyzed.
That really shows the push-pull, doesn't it? The slow, careful process needed for court versus the sheer speed and volume of digital crime.
Yeah, and what's interesting is that same level of microscopic detail applies to the physical evidence, too. It's not just about the paperwork.
Okay, let's pivot from the process to the evidence itself. Trace evidence, the tiny stuff. Hairs, fibers, paint chips. How does that work?
It's based on a really fundamental idea, often credited to Locard, but articulated way back by Hans Gross in 1893. He said, dust is like our environment or surroundings in miniature. Think about it. Dust isn't just random dirt. Dust from the desert is sand, plant bits. Dust from a ballroom, mostly clothing fibers. From a blacksmith shop, tiny metal particles. Every contact leaves a trace, linking people to places, people to people.
And probably the most dramatic trace evidence is often blood, right? Let's talk bloodstain pattern analysis, BPA. It's not just if blood is present, but how it got there.
Exactly. BPA is less about identifying blood and more about reconstructing events. It helps figure out what couldn't have happened based on physics.
Okay.
Analysts look at spatter patterns, transfers, voids where blood should be but isn't. Take cast-off patterns.
Cast off.
Yeah, that's when a bloody object, like a weapon, say a pipe, is swung. The blood flies off in an arc. The shape and direction of those tiny elliptical stains tell you the direction of the swing. And by counting the overlapping arcs, you can sometimes estimate the minimum number of blows struck.
Wow. And what about just one single drop if you look really close?
The shape tells a story, too. An elliptical drop has a tail or spines that point in the direction it was traveling. By measuring the width and length of that ellipse.
Geometry comes in again.
Totally. Basic trigonometry lets you calculate the angle it hit the surface at. Do that for several stains, and you can use strings or protractors or now computer software like Backtrack to figure out the 2D area on the floor or wall where the drops converged.
Okay.
And then taking it further, the 3D point in space they all came from, the area of origin. That can tell you crucial things, like was the person sitting or standing when they were hit?
That sounds so precise, like pure math. But BPA has faced criticism for being subjective sometimes. How can geometry be subjective?
Well, the geometry calculation itself is objective. The interpretation of what caused a particular pattern, that's where subjectivity can creep in. Was that fine mist really high velocity spatter from a gunshot? Or could it have been, say, X-rated blood coughed out? Or even a transfer from clothing?
Ah, I see.
The Indiana v. Cam case is sort of the textbook example of this problem. You had 8 different BPA experts looking at the same blood stains on a T-shirt, and they came up with 4 completely different conclusions about what happened. High-velocity impact, contact transfer, completely conflicting interpretations.
That's worrying. So how is the science addressing that, making it more objective?
That's the push now.
Okay.
Absolutely. Finding quantitative measures. For instance, there's new research looking at blood stains on fabrics under a microscope.
Okay.
They found that on certain knitted fabrics, if the blood was transferred onto it, like a wipe, the stain tends to stick more to one specific part of the knit loop, the left leg, apparently. But if it was direct spatter hitting the fabric straight on, the blood is distributed evenly across the loop structure.
Wow, that's specific.
It is. But it moves the analysis from, I think this looks like a transfer, to The microscopic distribution matches the known pattern for transfer on this fabric type. It's about finding those objective markers.
That level of detail, looking at microscopic things, it applies in other specialized areas too, right? We hear about insects, forensic entomology for time of death. What about crimes involving water?
Yeah, that's a fascinating field. Aquatic forensics, people like Paola Magni are doing incredible work. Her involvement in the Federica Mangiapello case in Italy is a great example. The victim was found near water, and the key was diatoms.
Diatom, those are like tiny algae, phytoplankton.
Exactly, single-celled organisms found in water. Here's the thing. If you drown, you inhale water, and those diatoms get into your lungs.
Okay.
But crucially, they only get transported from the lungs into your bloodstream and lodged in distant organs like your brain or liver if your heart is still beating. Your cardiovascular system has to be working to pump them around.
Ah, so finding diatoms deep inside the body means...
It means she was alive when she went into the water. It wasn't a case of being killed elsewhere and dumped. That objective scientific finding was critical evidence in securing the eventual murder conviction.
That's incredible. Just tiny organisms providing such definitive proof. But all this detail, this careful analysis, it takes time. And you mentioned time is often the enemy here. Lab backlogs, evidence degrading.
Exactly right. The sad reality is that the forensic value of evidence often decreases over time. It's perishable. Yet, because labs are frequently understaffed and overwhelmed, cases can sit for months, sometimes even years, before analysis even starts.
So how do you tackle that? Is there a new approach?
There is. It's often called the proactive crime scene response model. The core idea is to move away from treating every single piece of evidence equally, especially at the start.
Okay, so it's like triage.
Sort of, yeah.
Yeah.
It's about strategic prioritization. You identify a small number of items that seem likely to have the highest potential value, the most probative evidence, and you fast-track those for a first-pass analysis.
Try and get some initial leads quickly.
Exactly. Aiming for results that can guide the investigation within days, not months. Then, those initial findings, maybe a preliminary DNA hit or a ballistics link, help decide whether it's even necessary to do complex, time-consuming analysis on the other, maybe less critical evidence.
But is there a risk there? If that initial quick screen is wrong, could it send the whole investigation off course? Does it really save time in the long run?
That's a valid concern, and the system has to account for it. The key is the clear distinction between screening tests and confirmation tests.
Okay.
These rapid technologies like rapid DNA analysis or the Nubbin system for cartridge cases, they provide investigative leads only. They are not, by themselves, suitable for court.
So rapid DNA might give you a profile from a single source sample in, what, 90 minutes?
Right. And Nibbin might link a spent casing to other crime scenes in a database. These give detectives something to work with while the more rigorous, court-admissible confirmation testing is happening back at the accredited lab.
So the confirmation tests, the ones that have to meet those strict court standards like Daubert, still happen, but hopefully on a more focused set of evidence.
That's the idea. It's about using the science to generate forensic intelligence early on, integrating that preliminary data, or confirmed data when available, with the crime circumstances to connect cases, point towards suspects, or, just as importantly, clear people who are innocent.
That power to eliminate the innocent quickly, that feels incredibly important ethically. Do we have examples where that speed made a real difference?
Absolutely. The homicide case of Darrell Exner is a powerful one.
Right.
Timely DNA analysis did point to the person who found the body, suspect 2, but just as significantly, it rapidly cleared 3 other people who were under suspicion because they were nearby and maybe gave confused statements under stress.
Right.
Objective data quickly showed they weren't involved, allowing police to focus resources correctly and relieving those individuals of immense pressure.
That sounds similar to another case, the one with the 2 knives, where a father mistakenly identified someone in the dark.
Yes, a truly tragic situation. The father, understandably distraught and in the dark, misidentified a local young man as his daughter's killer. But trace DNA found on the knife handles quickly proved the father wasn't involved and, crucially, eliminated that wrongly accused young man. Later, a database search linked the DNA to the actual perpetrator.
And there's another one, the 2 men named Mark, who looked alike.
Same principle. In all these instances, objective science, especially when applied quickly, acts as a safeguard. Rapid DNA, fast database checks. They're not just about catching the guilty faster, they are fundamentally about protecting the rights of the innocent by clearing them swiftly. It prevents people from being unfairly trapped in a slow, agonizing investigation.
Okay, let's try and pull this all together then. We've got the need for absolute integrity, the chain of custody, the power of trace evidence, the drive for speed with new tech, and this crucial role in protecting the innocent. What does this all tell us about what it takes to be a crime scene investigator today? What kind of skills are needed?
Well, it's incredibly demanding. It goes way beyond just knowing the procedures, like how to bag evidence. CSIs today really need a strong educational foundation. A bachelor's degree in forensic science or a related hard science is pretty much becoming the standard and highly recommended
Why the emphasis on formal education?
because they have to be able to stand up in court and defend their findings against rigorous scrutiny, specifically the Daubert standard in the U.S. or similar standards elsewhere.
And remind us, the Dobert standard means.
It means the judge acts as a gatekeeper for scientific evidence. They have to assess if the methods used are reliable and valid. Is the technique testable? Has it been peer-reviewed? What's the known error rate? Is it generally accepted in the scientific community? The CSI needs the scientific depth to explain why their methods meet those criteria.
They need to be a scientist on the stand, essentially.
Exactly. They get one shot to process that scene perfectly, and they need the knowledge to back up everything they did and found.
And when you look at the crime clearance rates, what are they? Something like only half of homicides get solved, and even fewer for sexual assault.
Yeah, the latest FBI stats show homicide clearance around 50%, and for rape, it's tragically low, maybe 26% or so nationally. It really underscores the urgent need for highly trained, highly educated CSIs to maximize the potential of every single scene. This isn't just academic. It directly impacts public safety and justice.
Absolutely. The science has to be rigorous because the stakes are so incredibly high.
Couldn't agree more.
So we've talked a lot about how crucial that meticulous, often paper-based chain of custody is for physical evidence. That's signed, sequential trail. Now looking ahead, as forensics deals more and more with just massive amounts of digital data from phones, cloud accounts, smart devices everywhere, what's it realistically going to take to create a truly secure, globally accepted, tamper-proof chain of custody for digital evidence? Especially considering, as you said, current systems don't quite offer that complete, universally trusted protection yet. What's the next step there?